there's two differential equations that come up all the time in Physics C. One of them looks like this. So let's say second derivative of something, d squared smiley face by dt squared equals, and then minus a constant times smiley face. So this is saying there's a function out there called smiley face that if you take its derivative twice, you'll get that function back with a negative constant in front. And so this one, if you remember the one with two derivatives, it's going to give rise to sines and cosines. So your smiley face as a function of time is going to look like this, like a cosine omega t plus a phase. Again, if you take two derivatives, the cosine will become sine, or negative sine, and then the derivative of the negative sine will become negative cosine, so it'll give you the negative. And then taking two derivatives by chain rule will pull out two omegas. So that's the solution. And then the other thing to know about this is this repeats if, like, every time omega t hits 2 pi, so say omega times the special time period t equals 2 pi. And so what you can learn is that the period then is going to be 2 pi over omega. And so the classic example of this kind of thing, you guys have seen this before. The classic example of an oscillating thing, right, is a mass on a spring. And so if you say for a mass on a spring, acceleration is the force over the mass. So acceleration, which is d squared x by dt squared, acceleration equals the force minus kx over the mass. Acceleration is the force over the mass. So, well, you notice that these things are really the same. It's just that your omega squared is k over m. And so what will happen is you can just kind of cheat off of what we did up above. The period's going to be 2 pi. And then you notice, right, it's over the square root of whatever's here. Well, so if you go over the square root of what's here, it's going to be the square root of the reciprocal. So 2 pi root m over k. So this is kind of the general form, but this shows up anytime you see oscillations. And so one thing that I'm going to have you guys look at today, in fact, is the first of two little AP practice problems I left. You're going to see this show up. So it's going to look really similar to this, and so the solutions are, you can just kind of use this pattern to see the solutions. The second one, which we're not going to work with as much today, but I just to kind of flash it up here really quick. The other one that you see a bunch in Physics C, the other differential equation, is that if you take one derivative of something, d squared, or not d squared, d star by dt equals minus k star. This is saying there's a function called star out there that if you take one derivative, you get negative a constant times star. And so that's just a decaying exponential. So star would be some constant times e to minus kt. And so you can tell, right, if you take one derivative, it's just going to be minus k times this function, so minus k star. The place where you see that is with, just an easy example would be like motion with, just strict motion with drag. So you could say with drag, if you did like F equals ma with drag, then your force would be like minus bv if it's linear drag equals m dv dt. And so if you dink around with this, just playing around with this to transform it to look like this, it would be dv dt equals minus b over mv. Minus b over mv. Well, these are the same because you have, d star dt equals minus a constant times star. This is dv dt equals minus a constant times v. So these are going to have same solutions. So your v, if you just kind of cheat off of what we did up here, it's going to be some constant times e to the minus b over mt. So those are the two main differential equations that you'll see. Again,